Imagine you had a grid and 2 points, A and B. What's the shortest path that connects the two, and how do you prove it? Or, which path makes the ball drop the fastest in the presence of gravity? Just a quick little heads up though, this video will use calculus, which is differentiation and integration, and some multivariable calculus, namely partial derivatives. Do not let these topics intimidate you, however, as I'm quite new to these topics as well. Nevertheless, I'll try to make my steps as clear as possible. Without further ado, let's get started. Returning to the shortest path problem from earlier, we can clearly see that it should be a straight line, right? But how do we prove it though? Well, we know that we want to minimize the length between A and B, but then again, how do we do that? One way you could do that is to step back to a more familiar problem, which is to find the local minimum of a function. The motivation behind that is because, just as we can find the minimum of a function which maps a set of numbers to another using calculus, we could probably also find the minimum of a function null using calculus as well, where a function null is a function of functions, mapping one function to a number. In our case, our functional maps the function of a line connecting A and B to a number, its length. Now looking back at the simpler problem, we know how to find the minimum of this function. We first take its derivative and set the derivative equal to 0, because we know that the minimum point occurs when the gradient of the function is 0. And after that, it's just a matter of solving the equation for x. There is, however, a caveat. Notice how we got two solutions from this. This is because the gradient is 0 at multiple points, or stationary points to be exact. Nevertheless, we can still find the minimum by determining the nature of these stationary points, by using the second derivative test, for example. So let's first take a look at one path. We can write down the total length of the function as an integral. The reason for this is that if you zoom in on the function, it kinda looks like a straight line, doesn't it? We can call it ds, and summing up all these little ds's, these little straight lines, will give us the total length of one big curved line, and hence the integral sign from a to b. We can then break ds down into dx and dy components, little nudges in the x and y direction, and then use the Pythagorean theorem. After simplification, we're left with a crazy looking expression to put into our integrand. And so to recap, we've just derived the functional, taking in a function and outputting a number, its length, which we want to minimize. Just a reminder, by the way, the right side is going to be a number in the end because it's a definite integral. Everything up to this point has been quite straightforward, but how do we actually minimize this integral? And how do we even compute this integral anyways? I mean, we don't even have y, so how do we even find dy dx? Well, now I'm going to pull a rabbit out of a hat and introduce an odd-looking but powerful equation known as the Euler-Lagrange equation. It states that for any functional s that takes in the function q as an input, the path q will be a stationary function of s if and only if it satisfies this fancy-looking equation at the bottom. By stationary function, it means to either maximize or minimize s, which is to make it stationary, just like the points where we saw in the simpler calculus example from before, where the y values are either maximum or minimum. Next, let's look at the functional s. It's defined as the definite integral from a to b of L, where L is a multivariable function. You may also spot the q dot term inside it. The q dot term is actually just the q dt. Then, if you want s to be stationary, you want to have L to satisfy this equation down here. This weird looking d inside the equation is actually the partial derivative. Basically, it treats all the other variables as constants. As an example, let's say we have a multivariable function j to be 2x squared plus 3y. Partial j partial x will then just be 4x, because we're treating 3y to be a constant, and the derivative of constant is 0. With this equation in mind, we can go back and apply it to our length functional. I'll start off by writing the equation on the top right here. And I'll write down the L function, which we want to partially derive, with a fancy looking L, so that we don't get messed up here with the integral. From the definition just now, it's whatever is inside the integral. which is this square root term here. And I'll also write it as a binomial so that we can take the derivative more easily. Now speaking about derivatives, let's now find the first term in our equation, partial L partial y. Now notice that in our L function, there's no y's involved, right? There's only just y primes. So our partial L partial y is going to vanish to 0. Looking at the second term in the equation, we'll take the inner derivative first, which is partial L partial y prime. We can do that by treating the y prime as just another variable. Then we can use the power rule and the chain rule to find the derivative. Now I'll box these equations up for later use. And now, let's substitute these values back into the Euler-Lagrange equation. Putting in partial L partial y, which is 0, we get that d by dt of partial L partial y prime is equal to 0. Then we can substitute in partial L partial y prime to get this expression right here. Integrating both sides with respect to t, we get that this expression here is equal to a constant, which I'll call c, because the integral of 0 is just a constant. Now I'll box this up in red and we can move on. So from the previous segment, we got this expression involving y primes. We'll now try to get a y prime on one side of the equation, so we can integrate it back to find our desired stationary path, y. So I'll start off by squaring both sides to eliminate the square root on the denominator. And next, I'll rearrange the equation so that I get y prime squared only on the left side. Next, I'll take the square root of both sides to get y prime. And then notice on the right hand side is all just constants, so I'll call it a instead. Now that we've isolated y prime, we can start finding our original stationary function, y. So y prime is equal to a, and integrating both sides gives y is equal to ax plus b, which is a standard equation for a straight line. Well, I guess you should have expected that from the start. Nevertheless, I'll let you convince yourself that this is actually true by figuring out what a and b actually are. A small tip is to look at where our function y starts and ends. So yeah, we've proven that the shortest path between 2 points is a line. We're done, right? Not quite actually. This whole proof actually worked because I pulled out that equation from just now. Let's try looking at where it came from and why it's so useful in the calculus of variations. The problem we just looked at is just one of the many path optimization problems, in which we were minimizing the distance between 2 points. There are also other path optimization problems, for example the catenary problem, looking at the shape of a hanging chain, and the brachistochrone problem, looking at the shape of a curve that minimizes the time taken for a ball to roll down, just to name a few famous examples. I won't be going into these problems, but I highly recommend checking out some videos on YouTube, and you won't be disappointed, trust me. In all these examples, however, they have almost the same setup. A coordinate system, 2 points A and B, and an objective curve that links the two, which fits the criteria imposed by the question, which we want to find, and could be any shape, like literally any shape. And so let's say we've been given a general functional I, and we want to find a function that makes I stationary. Remember that the functional takes in a function and outputs a number. Start by assuming we already have the solution, and let's call it y of x. And here you assume that y of x is extremal, meaning that it makes I either maximum or minimum. What we can do next is to add some noise to the function, which is to make it deviate from the perfect path by a little, and see how it nudges our functional I. We can do that by introducing epsilon and eta of x, and I'll call the resulting function y bar of x. Now this term here can be thought of as a variation from the perfect path, where epsilon is just a tuning parameter, and eta of x could be any function, like literally any imaginable function that you could think of, but with only one condition, that is to be 0 at the boundaries, which is to say eta of x1 and x2 is equal to 0. Notice the similarities between this approach and differential calculus, where the variation is kind of like dx in a sense. As dx tends towards 0, x plus dx tends towards x, and as epsilon tends towards 0, y plus epsilon and eta of x tends towards y of x. Now let's take a look at a more concrete overview, and right here I have a Desmos graph set up. So this is my 2 points A and B, which is black and purple, x1, x2, y1, y2, and I'm using the previous example as my formula here for our assumed perfect path, which is a straight line. So let's hide these first, and we'll take a look at eta of x. So I've defined it as a quadratic looking expression here to make sure that it is 0 at the boundaries, but in reality, it could be any function, as long as it is 0 at the boundaries. Finally, this is my y bar of x, defined like so. Now notice how as I change on epsilon, the size of y bar changes. Now with that in mind, let's replace all the y's with y bars in our original functional. And notice on the right hand side, the x gets integrated out. So at the end, we're left with just an epsilon. So now our original functional depends on epsilon. And from calculus 1, we know that if you want I to be stationary, we want dI d epsilon to be 0. By the way, everything here now is in terms of y bar. And so to get back our optimal path, which is what we want, by definition we can set epsilon equal to 0. So this is what we get. Next, I'll substitute in our expression for I and bring the differentiation sign inside the integral and turn it into a partial derivative. This is also known as the Leibniz integral rule. So I've cleared out the screen and we can move on. I'll first take the derivative of y bar as it will be useful later on. Next, I'll set out for a multivariable chain rule. And notice that the only derivatives that involve epsilon are just these two. So I'll use the multivariable chain rule and replace them inside the integral. We can then simplify the expression by finding the partial epsilons. So partial y bar partial epsilon is equal to eta of x, and partial y bar prime partial epsilon is equal to eta prime x. Moving on, I'll simplify the hardest part of the integral, which involves an eta prime x, using integration by parts. Here's how I'll set it up. I'll set this to be u, and that to be dv. Then I'll integrate dv to get v, and differentiate u to get du. Recall the integration by parts formula. It's basically a product rule formula but rearranged. Then, I'll substitute the appropriate functions. So this term will be uv, evaluated from x1 to x2, minus the integral of v du. But then, remember our boundary conditions. At x1 and x2, eta is 0, so this term is 0 at the end. And we're left with this integral right here. Nice simplification, isn't it? We've turned it from eta prime into eta. Moving on, we can substitute our result from integration by parts into our integral. Also, notice that we're setting epsilon equal to 0, and what that does is to turn y bar into y only. We can do this to get an equation related to our desired function, y, that optimizes the problem. We're getting close now. It's starting to look like the Euler-Lagrange equation. So next, I'll factor out an eta, and let's see what we're left with. For an integral to be 0, the inside of the integral must also be 0. And, well, eta can't be 0, since we can't have 0 variation, or else nothing that we've done so far makes any sense. Well, then that must imply this term right here must be equal to 0. And so that implies that partial f partial y minus d by dx of partial f partial y prime must be equal to 0. And we're done. We've derived the Euler-Lagrange equation for path optimization type problems, saying that for a function y to make a functional I stationary, it must satisfy this differential equation right here. There are a few things to know about this equation though, is that this only works for path optimization type problems, but there are other generalizations, for example taking in higher derivatives of f, but the one on screen is already powerful enough by its own. Also, this equation does not tell you about the nature of f, whether it maximizes or minimizes I, so it will be up to us to work it out. Let's review what we've done so far. We first looked at the straight line path and some other optimization problems that involve the path, whether they be the shortest distance, the shortest time, or the closest to reality. We then assumed that y of x was the function that was extremal, and then added some spice to it. Then, through some reasoning, we got that the epsilon should be equal to 0, and setting epsilon equal to 0 gives us back our function in question, y of x. After that, we did some simplification and got this final integral from where we deduced that this part must be 0 too, which is the Euler-Lagrange equation. Now let's take a quick look at the history behind this. It's called the Euler-Lagrange equation because, well, Euler and Lagrange worked it out. It started in 1696, when Johann Bernoulli posed the Brachistochrone problem, and a lot of people actually tried to solve it, but it was actually in 1733 when Euler elaborated on the subject. Lagrange, seeing Euler's work, was largely influenced by him. In 1755, Lagrange submitted his solution for a tautochrone curve, which is a curve that makes particles fall to a point in the same amount of time. And this problem was not a new one in that time actually. Huygens solved it geometrically in 1659, but when Euler saw Lagrange's analytical approach, he dropped his geometric way of reasoning and helped Lagrange further develop his method. By the way, Lagrange at this period of time was just 19, whereas Euler was 48, who was a very famous mathematician with a big brain. A year later, Euler publishes the subject as calculus of variations, which is what we call it today, and Lagrange would go on and develop a new way of approaching mechanics called Lagrangian mechanics, and publish his own work in 1788. The applications of calculus of variations goes beyond the originally intended path problems. There are many interesting uses, but sadly I don't have enough time to include it in this video, but it really goes deep into physics, into many fields ranging from motion at large scales into quantum phenomena at tiny scales, also known as Lagrangian and Hamiltonian mechanics. It can also be used to solve for the equations of motions of infamous problems like this double pendulum, or this, or even this. Well, maybe not this, but it can even be applied to optics and astrophysics as well. The list goes on and on. It's very awesome, but I'm still stumbling along and learning. By now, you might have realized that the second example I provided in the beginning was the Brachistochrone problem. And with that, I'll leave the viewer with an exercise to find the equation for the Brachistochrone curve. A few useful tips include considering the conservation of energy, which is the interplay of kinetic and potential energy, and considering whether or not you should create your own coordinate system, which is like, should the system be centered at 0, 0, or should the y-axis be pointing up or down? And the third one is that you should get a parametric solution because that will be easier, and that comes naturally when you're evaluating an integral using U substitution. And the last one is to use Beltrami's identity, and it applies when the functional does not explicitly depend on x, i.e. there are no x terms inside the integral inside the functional. You could do just as well without it and get the same answer, but the Beltrami identity, shown here, can be used to simplify calculations quite a bit, where L is the function inside the integral, and C is just a constant. You could even try deriving it if you wanted to. Anyways, thanks for watching. I apologize if this video's quality is not on par with other videos on here, but nevertheless, it's still my first video. So here's a cat pic I found off the internet, and happy mathing!